Okay, so let us continue with our BCS calculation. And if you recall, we had written down the BCS Hamiltonian, where the first term in this Hamiltonian is basically the kinetic energy for a free electron, where Ck dagger Ck is the number operator, how many number of electrons are there in the momentum state K up, where K up, this arrow represents a spin up of the particle with energy Ek. And twice is because you are doing a counting for in the energy state K, both spin up and spin down electrons have the same energy, therefore this factor of 2 is coming here. And you have the other interaction term, which is Vkk prime, which is scattering from, basically you are creating a K up minus K down state by annihilating a K up, K prime up minus K prime down state, where this scattering from K prime up minus K prime down into this other state which is getting occupied, which is K up minus K down, is via this potential Vkk prime. So this is the basic form of the Hamiltonian, and we are going to basically consider energies Ek which are around the Fermi energy. Okay, so we will basically consider all the energy states. We will basically consider energy states measured with respect to the Fermi energy. Okay, and for energy states very far away, we are not interested anyways. So we will basically consider energies which are of EF minus EK types, where we are all measuring the energies with respect to the Fermi energy. Okay, so now let us go on with the derivation of this Hamiltonian. And basically when you are going to do this derivation, we will basically have to consider these anti-commutation rules, where Ck sigma, Ck prime sigma dagger, which is equal to Ck sigma Ck prime sigma prime dagger plus Ck prime sigma prime dagger Ck sigma is equal to delta K prime delta sigma sigma prime. Okay, this is one anti-commutation rule that we will consider, and the other anti-commutation rule is Ck sigma Ck prime sigma prime. This is equal to Ck sigma dagger Ck prime sigma prime dagger is equal to 0. Okay, this is the other anti-commutation rule, where this sigma or sigma prime represents the spin up or the spin down electron. Okay, so these are the basic anti-commutation rules that we will use now, and we will try and solve this Hamiltonian. Okay, now for solving this Hamiltonian, one basically has to again find the expectation value of this Hamiltonian and then try and minimize this expectation value with respect to some parameters. Okay, that's going to be the basic idea. So we will try and find out what is the energy state of this system and then try to minimize that energy state. Okay, and to solve this Hamiltonian, one will basically need a trial wave function. Okay, so this trial wave function was given by BCS for this form of the Hamiltonian. The trial wave function was given by BCS, and that's the wave function that we will write down, and we will start using that wave function. So your psi BCS is written as the product of case states UK plus VK CK up dagger C minus K down dagger okay, where, so this is the trial wave function, this is the BCS trial wave function. It was just proposed to try and see does it sort of solve for the expectation value. Okay, so you have to use this form of the trial wave function and see how does the system, how does the thing work out. Okay, so uk is, let me write down first vk. You can see that vk is the coefficient, is a trial wave function. You can see that vk, this term is related to creating k spin up minus k spin down state. It is this vk is the probability amplitude for creating, for the k prime minus k, the k spin up minus k spin down state being occupied, and that is related to ck dagger c minus k dagger, because it is creating this state. So vk is the probability amplitude for this state being occupied, and then uk is the probability that k prime up minus k prime down is unoccupied, probability amplitude that this state is unoccupied or it is vacant. So vk square is the probability amplitude for k up minus k down state being occupied, and uk is the probability amplitude that this state is unoccupied or it is vacant or vacant. Okay, so one can write that uk square plus vk square is equal to 1. Okay, so one very important relation which is satisfied by uk and vk is that it is 1. So we are writing the trial wave function as a product of occupied and unoccupied states. Okay, occupied states with some probability and unoccupied states with a certain probability coefficient. Okay, so we are writing them all out as product of wave functions with some probability of occupation and some probability of it being empty, and 0 is the vacuum state, completely unoccupied state. All the states are 0. So in the so this is the vacuum state, or we can also write it as so often the vacuum state, 0 is the vacuum state, and it is also written as sometimes you write it also as phi. Okay, so in some cases you can also write it as phi naught. So the psi bcs is also in some books it can be written as psi g to represent the ground state. In either cases these are just terminologies. Okay, and you should remember that if you apply ck up, if you try to annihilate anything from the vacuum state, it is 0. Okay, if you take the complex conjugate of it, then phi naught ck up dagger is also equal to 0. Okay, so these are some things that you should be familiar with. Okay, now again, so let us write down it let us write down psi bcs or psi g, whichever one, as uk plus vk ck up c minus k down dagger phi naught. Okay, now using this, let us try to find out what is the expectation value? So the Hamiltonian has two parts, H0 plus H interaction. The expectation value of H0 is this term, which is twice of K, Ek, Ck dagger, Ck. Okay, so let us find out the expectation value of H0, which is your psi g H psi g, or it is also psi BCS H0 psi BCS, whichever notation you want to use, you can use. Okay, and basically this is nothing else but twice of K Ek phi naught. Now this is where there will be quite a bit of there will be significantly long terms, and we will have to manipulate them using the anti-commutation rules. So let me try and do this a bit slowly. Okay, UK star plus, so this is the complex conjugate of the above psi BCS, so this will be VK star, and the order of your operators will change. And being Hermitian operators, so you have to also follow these. So now sorry, let me, before I write this expression, I have jumped a step. First of all, this part I am taking the complex conjugate of the wave function, trial wave function, Vk star C minus K up, sorry, C minus K up, C minus K down, C plus K up, and you have Ck dagger Ck. Okay, and then again a product of UK plus VK, Ck dagger minus K down dagger. Okay, now what we will do is that, so these are product terms, this is a specific K which is used, okay, and these are product of different values of K, both of these terms. So this is a product of multiple values of K, and this is also a product of multiple values of K. It is only this term which is a specific value of K. So for that specific value of K being a product, you can actually separate it out. Ek phi naught, you can separate out the specific K terms, and then for those which are not equal to that value of K, you can take the remaining product terms. So let me write that out. UK star plus VK star C minus K down, C plus K up, CK up, CK up. Then you take the specific term which is relating to this, you take it out of this product. Okay, UK plus VK ck up dagger, c minus k down dagger, and then multiplied by a product of all L terms not equal to k, because those k terms you have already taken it out from this bracket. Okay, from this bracket you have already taken out these terms for the k terms, so therefore inside the bracket you will not have this term. So you will have ul star plus vl star, c minus k down, c plus k up, ul plus vl, c k up dagger, c minus down dagger. I'm sorry. Okay, this will be L, c minus L down, c plus L up. Similarly, this will be c plus L up, c plus L minus L down times phi 0. Okay, this will be your vacuum. Okay, and the way we have manipulated it, okay, this is somewhat similar to, if you don't understand the above, then you can think of it in this form, that this, the way we have manipulated this expression is somewhat like if you have a product of three terms. Above manipulation is like x1 star minus y1 star, x2 star minus y2 star, x3 star minus y3 star. Suppose we have these three product terms, and then you have something which is like c2. I'm just taking some product of some terms, and x1 minus y1, x2 minus y2, x3 minus y3. Then this I can separate it out into x2 star minus y2 star c2, x2 minus y2, and then there is a bracket of the remaining x1 star minus y1 star, x3 star minus y3 star, and x1 minus y1, x3 minus y3. So this is just a simple rearrangement where all the terms corresponding to 2 have been separated out, and the terms which product terms, because it's a product, you can separate out the terms which do not contain that 2. Okay, that's exactly what we have done above. Okay, in the above we have just taken out the k terms out, and the terms which are not equal to k, which are related to ck dagger up ck, the terms which are not related to that, those we have taken out of the product. Okay, so now we can actually consider two separate terms in this expression. Okay, this is the first term. This is, let us consider that this is term 2, and let us consider this as term 1. Okay, in this expression. So first we are trying to, I'm just showing you a typical example of the calculation. So let us consider the term 2. Okay, the term 2 basically has something like ul star plus vl star, c minus l, c plus l, ul plus vl, cl up dagger, c minus l down dagger, the vacuum state phi naught. Okay, so this term 2, this was the term 2, I can simplify it to write it as minus modulus of ul square. Now I start taking terms together, phi naught plus ul star vl, cl up dagger, C minus L down dagger, phi naught plus VL star UL, C minus L down, C plus L up plus mod VL square, C minus L down, C plus L up, C plus L up, C minus L down, okay. Now in this expression we have to start using your anti-commutation rules. To simplify this expression we have to start using some anti-commutation rules, okay. So the anti-commutation rules that we will use is CL up, C minus L down is equal to 0, which implies CL up, C minus L down is equal to minus of C minus L down, C plus L up. Similarly, your other anti-commutation rule is that CL up dagger, C minus L down dagger is equal to 0. So this is equal to CL dagger, C minus L is equal to minus C minus L down dagger, C plus L up dagger, okay. Now if you consider these two terms in the above expression, if you consider these two terms, let us consider these two terms first, then UL star VL, CL up dagger, C minus L down dagger, phi naught plus VL star UL, C minus L down, C plus L up, phi naught. Now if you consider these two together, this will be 0 because this creates an this creates an L up minus L down state, because you are using CL up, C minus L down, and this annihilates the created state L up minus L down. So the net change in occupancy, of the L state is 0. Okay, so there is no change in occupancy of this state. Okay, so there is no change in occupancy of this state, and the state is basically going to remain 0. So the effect of this operator is not going to change anything in this state. Okay. Now let us consider this term. Okay, let us consider this particular term. So mod VL square C minus L, C minus L down, C plus L up, C L up dagger, C minus L down dagger, phi naught. Okay. Now if you use the above anti-commutation rule, first you interchange these two. So idea will be to bring the minus L and plus L terms together. Okay. So first you take the minus L is furthest from this, so you try to bring it close to that. So you do the anti-commutation rule, and then this above term will be getting equal to mod VL square into minus of CL up, C minus L down, C plus L up dagger, C minus L down dagger, phi 0. Now you interchange again these two. Again there will be a minus sign which will come. The minus sign came because of the anti-commutation rule. So because of this you will get a second minus sign. So VL square CL up dagger, okay, into C minus L down, C minus L down dagger, okay. This is acting on phi naught, okay. Now if you recall the anti-commutation rule, that CL up dagger is equal to 1, so CL up dagger is equal to 1 minus CL up dagger CL up, okay, just using the anti-commutation rules. And now you can use it in this expression, you can also put it in this expression, okay. And if you recall, CL up dagger CL up dagger into CL, okay, this is nothing else but the number operator NL, okay, this is just the number operator, okay. So the above becomes mod of VL square into 1 minus NL up into 1 minus N minus down, okay, acting on phi naught, okay. Now this is the number operator, okay. Now this can be written of course as, you can open out this product, mod VL square 1 minus, okay, minus N minus L down, okay, minus NL up plus NL up into N minus L down, acting on phi naught, okay. But remember that phi naught is a vacuum state, it has got no particles in any state, so therefore N L up phi naught equal to 0, and minus L down phi naught is also equal to 0, because there are no particles occupying either NL up state or N minus L down state, okay. So the number operator will just give you the number of particles in that state, but there are no states which are occupied, so none of these terms will give a non-zero, all of them will actually turn out to be 0, and hence the above expression will be equal to this term will be equal to VL square, okay, phi naught, okay. So now if you go back to your earlier expression, if you go back to your above expression, then here this last term becomes of the VL square phi naught, this contributes to 0, this contributes to 0, and there is UL square out here, okay. So this will give you, so the term 2 in your expression, you will have to go back to your video and see, but the term 2 in your expression basically equates to mod of UL square plus mod of VL square times phi naught, which is just phi naught as this is equal to 1. Okay, so the term 2 in your expression, okay, will just equate to phi naught. Okay, so if you recall that we had written down this expression, okay, it will be just phi naught multiplied of multiplication of 1 into phi naught, which is nothing else but phi naught. Okay, so there is nothing to multiply, so this multiplicative term goes away. Okay, now let us look at the term 1. Okay, in the next lecture we will look at simplification of the term 1.